Okay. I believe we're recording now. Pause and stop. Okay. Therefore, I'm recording. I can pause or stop. We're recording and we're in PowerPoint. Yesterday, I had a little trouble with Ron. Ron is injured. I think I'm gonna have to do something about that waiting room feature. Let's see. It's January 29th, and I guess the big political debate now is whether there will be witnesses at the impeachment hearings for Trump. Big news over the weekend was Kobe Bryant's death in helicopter crash. So I mentioned it last night. My wife's cousin, who lives in Los Angeles, made it a point to call a whole lot of people informing them of Kobe's death. It's like, well, I didn't think that was something that required a phone call, but he did, I guess. Uh, Brian, back. What we'll do today, last week we started on this DMAIC stuff, and I kind of think they could have come up with a better acronym, something easier to pronounce, but and then we'll start chapter 5 on which includes control charts and some of the other Magnificent Seven stuff. I looked at where we were and looked at what I had in chapter 5, and I thought I could go a little further than I described earlier. Or Tyler. Welcome to Tyler. So that's where we are today. Oh, sometimes the buttons respond and sometimes they don't. Maybe I should learn how that actually works. What we'll do, tentative schedule. I didn't throw together an assignment. I haven't done anything with that Deming article yet. I had some thoughts on scanning it and leaving it for you guys. It's inspiring. I don't often think about somebody who's working as a business consultant having sort of a heroic life, but that does tell a story like that. And I guess chapter 5 is methods and philosophy of SPC. That's a sort of an overview description chapter. The more detailed is control charts and the rest of Magnificent Seven. And Tyler again. Maybe somebody dropped a line there. 1 click, 2, 3.
I'm here.
Okay. All right. It's the book I have in the bag next to me. This is on the shelf in the room. Many of my older slides come from this. They're a little different color. And this is one of the books listed to new edition. Um, and I actually have uh, older edition yet, the fifth. I think maybe I got a third too. It just used this book a long time. And who else? Cole Cameron. Cole sent me an email talking about, oh, don't remember what now. I haven't responded yet. Hopefully it's in both classes. And the furniture's moving above us already at 6. It was pretty well after 7 when it started. Ye- Yeah. Uh, okay, I still got the same locations as last. Haven't decided to move me to another office yet. Okay, web resources, use D2L, get an email about logging into the class. I uh will contain we'll have some links about connections to Zoom and same Zoom account. Many of you found it with D2L under content. You can log in you can watch videos a few different ways, um, and under a section called communications in Zoom, you can get there as soon as I can. For example, you can get to last night's class from there, but at none of the other places on D2L because somebody didn't work on getting those up last night and today. Uh, who might that have been? Well, there isn't anybody else assigned to do that. uh, yeah. And I did notice I put the exams, don't always like having two exams next to each other, one on a Tuesday and Wednesday. And I realized when I looked at both my tentative schedules, I had exams, one on Tuesday, one on Wednesday. And I thought it'd be better to move it in this course uh, to the next week because um, exam one is on Ash Wednesday. This way, if I move the other one on Tuesday night, uh, it would have been on Mardi Gras. Uh, and chat, we got a chat message. Okay, that's fine. Uh, if you're gone for a conference, we can make arrangements for we can make arrangements to have you make that up as the distance students do. So no no big deal. The distance students uh, take the don't have to take the exam on the scheduled date. So um, and actually the on-site students don't either. But thank you. Okay. Um, We used to be extremely generous on when you could take exams, and however, now, uh, however, now, administration has just sort of decided that uh, getting things in late is not something they like to do anymore. Uh, it's almost like an administrative war on late grades. It's, it's just the easiest thing to do. Uh, let's see. Guess you guys can think about when spring break will be. Right? This seems to work on the second try. Two exams and end assignment. Each of these three items will be equally weighted. Okay. Ace is here. Amiati, I think. I have somebody in my OLC class with the same last name. Uh, Amiati. Koi Amiati. Maybe a relative. I don't know. Um, may do some suggested problems. I didn't go through those. The book doesn't directly reference our in the statistical quality control sort of world. R is not all that big a player, just because some of the commercial software companies have sort of had big niches. That's um, uh, however, the DMAIC process, one slide for that. So I've stepped back a little. Some of these are review slides from last week, including this one, which summarizes all the tasks on the slides and then realizes there's a toll gate at um, each step. So if we're studying these, we want to realize that there's um, a lot of formality set into this. Although if you can take guidance from this, even if you don't have a formal project. Probably another chat. Would you have other suggestions as students here offer low cost options, jump for $30 for a 3-month license? Uh, well, I don't have JMP, so actually, for much of what we do with control charts here, uh, a pretty good, and the graphs in the textbook, uh, pretty good uh, control chart, a pretty good spreadsheet. Well, sort of common spreadsheet skills will let you make most of the charts for the control charts. and a few of the equivalent plots to some of the other graphs. Excel is acceptable. Yeah, you can get most of this stuff done in this book with Excel. Um, with uh, sometimes you have to be a little careful, but it it throws up a graph kind of crudely, kind of quickly. Uh, all you have to do is sort of put the information in the right columns, and the calculations are fairly straightforward to do. Probably should maybe go through a few of these graphs in Excel in chapter 6. Probably be easy enough to do. It's, yeah, and I don't. Hmm, I'm just thinking. I haven't really tried to do graphs in Google Sheets. Has anybody tried to do those? Really? Okay, so you can plot 4 lines on a chart pretty easily. Okay, okay. Well, I had um yeah, I had somebody send me a file in Google Sheets. Oh, and I was supposed to check to see if some of my students were on a list, and the list was sorted by not not by name. It was sort of unsorted. It might have been like student number or something, and I I had to sort that today, and it's different. However, it wasn't terribly difficult. So uh, yeah, for the students that are on site, they the undergrads, they uh, get a computer and it comes loaded with Excel already, and so that's um, kind of easily assumed. Uh, um, but knowing that Google Sheets is free and Excel you have to find some licensing for, uh, it now becomes a different question if we what you can do in Google Sheets. Kind of uh, okay. We went through this already. What parts of things are in the define step, and some ideas of setting things like making a business case. Is there enough value in what we're doing to support it? And limiting what we're going to do in a scope setting. We also have this um, uh, a CPOC diagram could be helpful in that part, and some of the details in what we had in a defined toll gate. Check to see if we're actually done. And then we had a measure step, and some of the things in this uh, checks textbook would be useful. and the measure toll gate we talked through. Um, and we finally got talking about an analyze step. And this is uh, around the last step we talked about in class um, last week in determining um, um, enough understanding of the process that we can, in a sense, um, know how to make the right adjustments to fix it or to verify it. Um, and this is where we finished last week. And I erased the done for the week comment. or should I say deleted? In PowerPoint, when you take that hand drawing off, it's more like a delete than an erase. It all goes at once, or it all stays. It's like, what's that? It's that next door, or it's that upstairs? Okay. Wow. Oh, okay. Wow. Well, that's different. Usually we just hear the maintenance staff in the halls. Now, I, for those of you who are in distance, I've got my face mic'd, so you can't hear the students in the room, and hopefully you can't hear the people dragging the furniture upstairs. And now, very rarely, there's a meeting in the other room where people seem kind of excited about things, and they're speaking a little more loudly than you might expect in a classroom setting. But uh, it's it's just starting to get on the edge of being disruptive. There are a couple of guys in the room. I guess the first week we had a bunch of people here. We had like 9. Yeah, yeah. On exam day, a lot of people show up. Oh, at all kinds of times. I, I don't know. Looking at uh, talking about rules on things, and I think the fun part of distance ed is going away. It's this idea of when people are sorting things out. Now it's the regulation. You should be. This is what must do. Okay. Next, the improve step. Uh, we can process redesign to reduce bottlenecks. Uh, we talk about it. We talk about these things having a different meaning depending on what time of day it is or what class you're in. Process here may actually mean something a little different than it does in a manufacturing class or a um, operations planning class or a simulation class. Here, processes are um, from the entire flow that we're including in our study. So a process isn't what happens at a workstation. A process can be across multiple workstations, and we can move tasks from workstation to workstation, for example, to balance things to reduce bottlenecks. We can also look at what goes on at a particular workstation to see if the tasks are there. Um, Bottlenecks, though, are we learned last fall that bottlenecks are actually a design feature of the network that we get to, in some senses, we get to design a detailed process on how long it takes. Sometimes the physics of doing that is kind of hard to change the times. When I worked for GE, we used to uh, melt a couple pieces of glass in a vacuum furnace and seal niobium to synthetic sapphire, and yeah, uh, and you kind of couldn't like go or fiddle with that so much on your own. However, uh, some of the things in that process, how many people actually assembled the parts on the fixture to go in the furnace and took them out, and that you could fiddle with pretty easily. Um, and what's done when and how to design the sort of meta process and reduce bottlenecks. And here, bottlenecks is sort of in a common language sense rather than last semester where it was specifically defined. So, uh, 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 mistake proofing, uh, very important thing. As we're studying this group of processes, we can sometimes realize, um, you know what, if a person has to uh, adjust a nut, for example, give them only the wrenches that fit instead of putting the whole toolkit out. If it's a torque wrench, have it make a noise when it's in the right uh, torque to the right level, instead of having somebody remembering. So yeah, can realize that. Statistical tools for improvement, uh, design of experiments. Yeah, it, it is useful here, and the author is a big advocate of designed experiments. Uh, they definitely do have their place, and one of the biggest, most important ones is, of course, in agriculture. Um, how to uh, grow the largest yields of rice or corn or wheat or or other food items. Um, Less, and in chemical processes, making the adjustments on those for better yields. They're very common. For fixed parts manufacturing, doing something like putting the settings on welds, it works well. Um, I, there are a lot of people who advocate it more than that I've seen success with, but it is there, and this author has a book on design of experiments. It's an advocate for it. Design of experiments is sometimes described as DOX, sometimes it's DOE, and it can be applied on a physical process Uh, the computer models of the processes have different statistics, and the design of experiments doesn't fit quite as cleanly. And there are different kinds of computer modeling systems. Again, what we mean there depends on the time of day. Okay, so uh, a pilot to test solution and confirm that it'll solve the problem. So when we talk about piloting, again, this is sort of a common language use of piloting. Uh, some organizations have strict definitions of what piloting is. So what's it disapprove? Um, check the documentation on the solution, um, and documentations on alternatives that were considered. Um, this is actually kind of nice. You sort of get credit for finding your dead ends um, in in this system. It um, yeah, why did you have to try all this other stuff? Because we didn't know it was going to be worse. Uh, okay. Right. So do as much testing as you can to see if you can make your improvement as practicable. Uh, and there are massive regulatory environments in certain places, and uh, some people, make careers out of just fighting regulations. I've just um, and standard business practices. Uh, I uh, somebody uh, somebody found a mil spec when I was working on how to make a control chart, and I kind of laughed. Why does this have to be regulated? It's just when we show you that later in the session, it's going to be there's a there's a spec on this. It's like uh, okay. The control step. So this by control we mean control more closely in a management sense than in a, a double E controls lab kind of sense or ME. So, all right. Depending on what time of day, words mean different things. uh, and and I I think I didn't get a job one time because I didn't know that accountants used variance in an incorrect manner that will have negative numbers. So, well, what can't have negative variance. Uh, so control step includes that. Uh, we have this idea of a process owner as someone who's responsible for it with a process control plan. So you have something to be fixed. What do you do to verify that your fix stays in place? Um, training documents should be provided. Okay. Um, in quality control as sort of, or quality as sort of a profession. The idea of auditing, where you do not so much regular inspections, but periodic on the order of yearly, quarterly, half year, every 2 years review of documents and procedures of how things are done, um, and being followed. So if you have changes to your process and a control plan, you need to modify things so that the audits will stand up correctly. Or you don't do it and wait for the folks on the audit to complain about. uh, and these are analogous in manufacturing. We have them, and they're somewhat analogous to like accounting audits. I had a friend who uh, when I lived in Minneapolis who did a job as an auditor for Sherwin-Williams, which has many small stores across the country, and I'm thinking it was thousands at one time. Um, and we had kind of a strange relationship. We met in church. We were both from Cleveland and working in Minneapolis. He co-opted with the company that I was then working at, and was currently working with the company my father had worked for like 35 years at that time. So it was, so I kind of knew each other in some strange manners, though. Yeah. Uh, uh, yeah. Um, so transition plan to the new process might include a validation step. Okay. So validation here in common language usage. Although in some classes, validation is a technical term. Okay. Control tollgate. All right. You have this project charter because we actually have this thing called a project. And in the odd years, we talk about what projects are and project charters. Uh, okay. Uh, is the process control plan complete? Are procedures to monitor it, such as control charts in place? Okay, we do that. Do we have documentation? Um, Lessons learned ongoing? Uh, so opportunities not pursued list. Huh. Yeah. Uh, you might have ended up um, purchasing a new technology for this process that might be valuable other places: measurement, recording, statistical analysis, sensor, and so a few case studies. This subject matter of the book is taught in um, business schools also, um, most often required in industrial engineering programs, um, electives in others like ours. Um, Case studies in business schools are sometimes the core of the study. It just read things and write about them. Just uh, as opposed to doing calculations and finding answers in a book. uh, uh, so litigation documents, improving on-time delivery, improving service quality in a bank are the case studies there. So did we go through these learning objectives, the importance of selecting? We talked about that for improvement activities. Essentially, in viewing things in a large organization, this was started at Motorola, when actually Motorola, uh, I guess for many of you, when you think of Motorola, it's just one of the lower level players in cell phones. Um, however, when I was your age, no, okay, so, they were a big name in consumer electronics across the breadth of consumer electronics. So, um, which didn't really include cell phones. uh, uh, so a fairly large organization, and there's a legacy of broad broad technologies there. Um, so even in a fairly modest size manufacturing plant, you know, a few hundred people working there, there are many things going on, and um, where you seek to improve things, but you only have a limited set of resources to do these in-depth kind of studies, you've got to make a justifiable argument for those. And those show up in the defined stuff more in detail. And, well, toll gate reviews, guidelines, and keeping people from jumping ahead. Um, and, okay, chat. Okay, Ron. Okay. Uh, you were there in 97, 98. Six Sigma training at Motorola. Okay. Back 97, 99. Well, that's hopefully you can correct me when I'm saying things wrong then. Okay.
Sadly, my own memory isn't that good either.
Okay. Ron commented in my ear that his his memory doesn't get all the details to sort of to be helpful correcting. Yeah, I remember some big details about 98, 99, but not too much about 97. Uh, okay. Um, I don't know if I left it on the intros, but 98, 99 was when I did my Fulbright in the Philippines. So some of the stuff I do remember, 4 classes in a row, no air conditioning, in the tropics, 200 feet or so from the seacoast, climbing stairs and changing buildings between every class. And then walking home for lunch. It's like, yeah, that uh, yeah, yeah. One of the department heads, I've worked in 2 departments, made it a point to tell me where where I could go to get water if I need to. uh, yeah. Yeah. Oh, one classroom I was in, it was the noise was like really bad. The oh, okay, technology, you don't have these here. Large part of the transportation system, including public transportation, were motorcycles with sidecars. Of course, they were not necessarily designed well. I mean, the gearing was such that people have to be switching gears and making noise, and then they were often like dirt bike kind of designs, and uh, the building was like right up against a narrow sidewalk from where the road was. So, uh, and there were windows on that side. It wasn't real nice, and um, I ended up not using the board in there because we only had like 4 people, and it's almost like it write out a page and everybody could see. Uh, yeah, that was uh, okay. Um, all right. Yeah. Okay. Rem- remember remember some of the things about 98, 99, and when we got back in September, my wife had um, a cooking accident where she burned her feet, and so I yeah, so she was that was really difficult. Okay, some things about where when to use it, and well, a little bit about how it fits into Six Sigma. Uh, Six Sigma does include, this idea of selecting projects and for usage, and does train people to use techniques and measure, analyze, improve, control. So much for that. Methods and philosophy of statistical process control. Um, Overview on methods. Most of the rest of the book is details. And the um, there'll be a few things we'll skip out of this section. 5.4. Some of my research activities will fit there, and you'll get burdened to listen to talking about me on my own stuff. Yeah, I think this is a good idea. I was like, yeah, somebody else. Why'd you pick that stupid name? I spent a lot of time coming up with that. Um, let's see. We'll maybe talk a little bit about service industries and so forth. Um, well, so listening to the other room, we went through. Okay, chance and assignable causes. Essentially, oh, we have another discussion I should throw in. Now maybe it'll go better with chapter 6. How um, you can put control charts in a general discussion of statistical inference. When you introduce statistical inference, at a beginning stats class. Well, I can do it, and some of the people who went to a conference listened to me can do it too. But and yeah, and there, in a certain sense, when we talk about chance and assignable causes, assignable are things that you could say are uh, outside of a confidence interval or uh, statistically different in the hypothesis test, which turns out to be sort of the same thing. And then I guess the sort of depends which class you're in. uh, Explain the statistical basis of assured control chart, including choice of samples. Okay, we'll talk about that. Rational subgroup concept. Um, the control chart idea sort of sits between the level of inspect everything or inspect nothing and trust that you don't. So how to sample in an ongoing process. Um, some of the other things in SBC, histograms. I hope in your statistics class you had that. I I honestly don't think it's a statistics class if you haven't. Uh, uh, all right, you haven't heard me teach statistics as an intro class yet, but uh, um, ow. I'm thinking about what I did Monday night, and it seems so sacrilegious. But um, the textbook there introduced histograms, but at such a less important level, as opposed to more often doing table calculations as an emphasis. And um, okay, it, it's a friendlier way to friendlier in the sense of people have poor math backgrounds to ease them into the class where they have to do calculations. Um, uh, okay, yeah, what did I do on the other? Check sheet. You've seen these things and they seem like good ideas. Pareto chart, maybe you haven't. Those are actually kind of fun to do. Abby, welcome to Abby. Um, um, Cause and effect diagram, again, something kind of useful. You may not have seen these. And defect concentration diagram, when you see them, you'll think they're good ideas. Scatter diagrams, you probably did these and you just sort of call them plotting points, but no, seriously. I mean, probably in like elementary school, you had a little science lab, somebody told you to plot this against that, and, and you did it. Um, and the control chart. Well, we'll have a few chapters on those, and um, phase one and phase two. Um, Sometimes we do a control chart when we're just testing to see if a process can work for us. Putting on the settings, running a few things, um, and uh, other times explain the average run length for a control chart. Uh, Uh, Average run length, it, kind of the term defines itself. Uh, when we do this sequence of things like hypothesis tests or confidence interval checks, and we do them in sequence, we can make use of the sequences to tell us things. Uh, the authors claim this. SBC can be applied to any process. Well, again, if you define process right, uh, you can define it with a certain property, right? And these seven, no, don't say that. Uh, go. Uh, oh, that. What am I trying to do? Give me my pen. All right. Most often, other places will call these seven basic tools. Okay. Uh, and as defined in a book by Ishikawa that started the quality circles movement, um, known as Guide Ishikawa's Guide to Quality Control. And it had these seven tool yeah, these were all in there. Seven tools, um, uh, detailed, explained with examples, with the idea that factory workers could come together and work on improving their own processes, gathering their own data, and making these studies. They can both learn the things and improve the processes in an ongoing manner. In a study group called Quality Circle. Um, nice idea. In a business sense, it doesn't work everywhere. Um, you have to want to listen to factory workers in making your process changes. Not every organization does that readily. Uh, uh, the other thing is uh, the academic levels, although they are pretty modest here on these charts, end up being a bit demanding for some people who've been out of school and just had some relatively well-defined jobs in a factory. They kind of forgotten how to do a lot of math and things. Well, I, you can get in a situation where, you know, your spouse handles the money and you go to work and it's nasty and uncomfortable and you get a decent paycheck for it and your life all plays out nicely. Uh, uh, at one time that was true. I don't, I've, I've been, you can be 50 and, you, uh, you haven't done a lot of calculation work for like 40 years and it all worked for 15 years and it's all working out nice for you and somebody tells you you're gonna have to be able to do all these calculations. So that that was a problem too. uh, Okay. Histogram, you've seen those. You've likely seen stem and leaf plots. They're usually in the, okay. 381, it's there. Check sheet, Pareto chart, we'll show you that. Nice idea, cause and effect diagram, we'll see that. Defect concentration diagram. Once you see it, it'll all make sense. Scatter diagram, you've done. Control chart, we'll spend most of the class on. And what do we have? A process is operating with chance variations is said to be in statistical control. Okay, the changes in there are chance in the sense that they're random and we can't easily make changes that that will affect them. Yes, we can buy a new machine and make it more precise. Um, but assignable causes are things like um, you actually make a mistake, put the wrong settings on the machine, uh, have parts that are out of spec, have um, things that aren't behaving in a regular manner. It's out of control. So in control and out of control are technical terms in so what we have is we make things and we imagine it's a process and it has a distribution and this is a we can imagine each part having its own when we make it when we make a part we're randomly generating a number and all these numbers have the same statistical distribution chance of going that way and if they're all the same distribution we're in control if things are going on that cause the distributions to change like every so often somebody puts the wrong setting in the machine or sticks the wrong part in or uses the wrong treatment things change they bounce out of the way uh, either the most commonly the center point or mean can move other times the standard deviation of the process can change can imagine a machine with like a bearing wearing out introducing more variability and also introducing more noise right okay uh, nobody's here heard worn bearings no okay all right uh, okay what's on a control chart they kind of look like this and it has this thing called a center line and it has an upper control limit and a lower control limit and it has a plotted statistic okay uh, and and we define the control chart as if the point that we plot the statistic that we get from our process is within the control limits we say in control don't do anything about the process leave it alone call it good and go forward right uh, the point if we go this test statistics goes outside of a control limit we know we know that the process we've judged in a sense that the process has changed we've made our judgment under practice even if it's because it's common to say 1 out of every 378 times this is going to go out when it's working correctly we've made that judgment and we're going to act. We're going to act as if the process has changed based on our statistic. And acting as if the process has changed means, should mean, you tell somebody to do something to fix it. Okay. It could be, stop a machine, make a phone call. It could be uh, take these uh, take these things apart, put some other things back in. It could be a whole list of things. And it is good practice if you're running a control chart to actually have an instruction for somebody of what they should do. Now, when I first took my first quality control course, when I was about your age, they didn't tell us that. They just said it was out of control. But now it's good practice. If you're going to actually put up one of these control charts and you're going to tell somebody it's out of control, you should tell them what they should do. Stop the machine, make a phone call, run a diagnostic, push a button, yell at somebody. I don't know. Blame the Republicans. Oh, yeah. Uh, control charts and hypothesis testing are connected. Yes. Yes. I'd argue that they're the same expression, and I think I might do that next week. I might dig up my um, discussion from I give to my lower level classes and burden you guys with how I explain that. And there's a good story too. I I ended up looking up something that there's a uh, all right. So we can have a real the average flow width of measured photolithography process, um, and we sample uh, five wafers, and our process mean is 1.5, and our process standard deviation is 0.15. And I don't know if this is dated on how chips are made these days or not, or anything, because I like know nothing about this stuff. So, all right. Uh, there have been um, some books I've had, and they talked about the sizes of pistons, and it's like, oh, what kind of engine has pistons that big? It's huge, you know. The instructor was like, statistics class. I don't know anything. uh, I don't know. I don't always have to know anything. I saw an article today about Donald Trump was talking to um, some industry folks from trucking business, and he didn't know that semi trucks ran on diesel, and he didn't know that you couldn't put gasoline in a diesel engine. It's like, well, Rex Tillerson had a comment about him, the guy from ExxonMobil. I can't quite quote him on that, but not when I'm being recorded. Yeah. Note that all points plotted fall outside fall in the control limits, so the process is in statistical control. So, uh, good news. everything's working fine, and they look like this. So let's see. Process mean is, so we'll do a little bit of calculation here, and um, sort of backing into the details of how do we get this line of upper control limit here and lower control limit there, and when we're just given these two numbers. And we'll show, oh, a chat. Rex Tillerson has an engineering degree versus Trump. Oh, whereas Trump bought his from Wharton. It's like, whoa. He has an economics degree. Yes, that's true. Uh, well, we'll see. We'll see if I have to ask for Republicans for money. I'm in trouble. No. I don't know. Uh, um, we have, we remember our definition of the standard deviation of the sample statistic. The mean is this, the standard deviation of the observation divided by the square root of n, the sample size, and we compute that. Now, we actually can use our z table then to talk about, to do something like produce a confidence interval on that mean, okay? And we did that. We could also talk about the z table as multiplying it, a number, reading the z table from the center to the edge, or if you were thoroughly into R in your statistics class and wouldn't use a table, I don't know if there was some tall, skinny guy who'd slap your wrist in class for that. You apply Q norm. Okay. Uh, all right. Well, uh, we'll see. You apply Q norm, and you'll get this Z alpha 2 function. Okay, and if you had the right book, so you would then be able to see, 1 minus alpha percent probability that X bar would fall in that zone, and then we could actually make that a control limit. In practice, we kind of go to the edge of our common Z table and pick a 3 because it's near the edge. It isn't exactly like that, but it's pretty much that. And it became the common practice to use 3, and we'll run our control limits at these points. And these are called 3 sigma control limits. And it's common practice to use a 3 there instead of looking things up at the table. Now, so here's this general model for a statistical quality control chart. And if you love reading the stats theory, this will get you through the next much of the next 3 chapters with just having to derive a little bit of, well, of just looking things up in that back table in your math stats book. Oh, you guys didn't have that, but there are tables of distributions and uh, formulas for means and standard deviations all listed together um, in a math stats book. And are they in the engineering stats book? Well, I'd have to look. I don't look at those. I don't teach that class for. Well, it's been a long time. I uh, okay. So we have some kind of sample statistic W. Okay, come up with some kind of statistic. Mean, variance, standard deviation, a proportion, uh, a max of a set of this, a min of a set of that, range, a range of this many observations. Any of those things work. Um, and if we can figure out the a theoretical mean of that statistic and a theoretical standard deviation of that statistic, we're good. And the other thing is you can cheat the system by not actually being all that theoretical on getting those means and standard deviations. So you can like go to a lab and come up with these and draw a histogram and do it with a data table and come up with something you trust is a mean and standard deviation of some kind of measured statistic. Um, then you're all good to do this control chart. All good. And we can play all those games to tell people when to leave the process alone and when to go tell somebody to do something or not. And that's actually a big decision. Why? People like to think they're important and useful. So they like fiddling with stuff. Also, some people are like lazy and don't want to do stuff. Now, unfortunately, the processes we can't design the processes to match the person. So we have to we would like to have the processes to just let people be lazy and figure out what else they're going to do, or to look at something else. There's just certain things you ignore in life, right? You don't often when you buy a food product, you trust that what's in the package is what it says it is. Okay, and you just do it. Now I had fried rice for lunch at the Chinese restaurant, and I could taste no soy sauce in that fried rice, and I didn't think that was right, but because when I cook fried rice, I believe there should be a mixture of garlic, soy, and egg for fried rice. It's not Chinese style fried rice if those are things are not present. So no, don't. Okay. Uh, anyway, so this is it. We can play those games. And L is sort of an arbitrary number, and it's very commonly 3. And um, talk about what people would do to get random numbers. I haven't told this story for a while. Uh, Sure control chart. Actually, that magazine uh, I brought in another issue, Quality Progress. One time I had a cover of Short of the actual way that random numbers were generated to make an argument that this was sensible. Um, Stewart got buckets of ping pong balls and labeled them, okay, with various numbers so we could have distributions of certain patterns and use those to sample things to see that if he used means, if he didn't have symmetric, normal looking distributions, would would this method work? He didn't know that, so he just sampled with pulling balls out of a bucket, which doesn't seem to be all that adventurous. But anyway, turns out that um, probably uh, somebody um, probably uh, um, actually the calculations he did weren't all that hard to do theoretically because he just worked triangles and well-defined shapes, and if you could integrate, you could understood the relationships, you could get them. So um, anyway, uh, uh, so he proposed this and came up with this principle and used this thing that's like a hypothesis test. There was a it was kind of on the sloppy side to see if this would all work, and it did. Um, and in the 20s, it's the kind of thing you do at Bell Labs. Um, uh, some things you might remember from statistics, that the distribution, if you have a normal distribution, um, the distribution of the mean becomes tighter than the observation. Um, and it and there's again the formulas we used, 1 over the square root of n is how it works, and if it's normal and you average it, it stays normal. uh, and you may recall hearing something like that. But uh, and if distributions are well behaved, when you average them they look normal, um, and they look more normal depending on um, how well behaved they are. Uh, well behaved, I guess, is a statistical equivalent to sufficiently nice in a math class. Wait. Uh, well, it's well behaved in statistics. It's sufficiently nice in math. It's same thing. Okay. Uh, um, Most important use of a control chart was to improve the process. In generally, um, most of the time, people aren't taking enough care to put things in statistical quality control. Okay, just letting things get kind of sloppy. What they do. Um, I I had raisin bran this morning, and I didn't measure how much I put in my bowl. Okay, uh, and nor did I uh, measure the amount of milk I put in. So uh, uh, now, when I make instant coffee, I supposed to measure it, but sometimes I just shake them. uh, so that's important. So if you're having a process that appears to be giving you a problem, if you can put it in statistical quality, in statistical control, uh, you probably will help it. And when we're doing that, uh, if you're attentive to the control charts, you can guess at what have made the changes based on the history, what was going on. It went out of control, and went out of control when the shift changed, and and the old guy came in who knew better. No, okay, uh, that's what that's what you young guys laugh at. If I would told it the other way, you wouldn't have laughed. uh, so, so this is when you don't say "Okay, boomer." You have to say "You're wrong, old man." These causes can be eliminated from the process. Variability will be reduced. The process will be improved. So we learned last fall in operations planning to fight variability, and this is part of the fight. Okay, part of the fight. Um, the improvement activity using the control chart is illustrated in Figure 5.5. Notice that the control chart will only detect assignable causes. Management, operator, and engineering action will usually be necessary to eliminate these assignable causes. Okay, somebody has to tell somebody doing something wrong. Okay, occasionally, but generally, these aren't things that cost a whole lot of money. And when I took the class, that was a point of view, and I took it from General Electric. No, the original name that my employer was General Electric. The guy's name was Carl something, right? Remember Carl Mensch? It's been over 40 years. I don't don't remember my instructor's names for 40 years. You probably won't either. Who was that guy? Meta what? I don't know. uh, yeah, I don't think I'll bother to chase you guys down 40 years from now to see if you did. If I'm there, if I'm 102, I'll probably be thinking of other stuff. But yeah. Um, so we have a process that has inputs and it has outputs. We have a measuring system and it feeds back. And if we can detect an assignable cause, we can identify it, implement a corrective action, and follow up. Okay, with our measurement system. And this is how a schematic of how um, process improvement should work. Um, things go out of control, we detect an assignable cause, and we can see what did it and correct it and follow up. Um, uh, we failed to tighten a tool at a sufficient torque. We had we identify the root cause of the problem. There were no specific torquing instructions for the operator. We now give a torque instruction uh, to this, and we both train the person and give the new tool in place to get the torquing. Um, however, we do that, uh, and we go and we check to see if the new tool is still there and people are still using it and the documentation is there and the training. Uh, uh, and let's see, we can actually have a series of questions in our um, we talk about an action being taken when we're out of control. It can be a sequence of questions. So out of control signal on the chart. First thing to check, was the data entered correctly? Um, why not? Um, which which part of the test failed? Um, oh, they don't tell you an X bar in our control. What we do with an X bar in our control chart is we measure both the mean and the range of a small sample. So we have two things. So if we go out of control on a range chart, we have a different instruction. Uh, and you now tell somebody to uh, run down the hall screaming. No, okay, no, no. Factory workers don't scream um, and run at the same time. they just they just talk to anybody who'll listen because nobody listens now. I think that's why they have co-op students, so they can listen to the factory workers whine. No, and they can tease the young guys. It's like, yeah, our temperature settings and time settings correct? No. Okay. So yeah. Uh, so there are things you can actually check on the machines. Uh, is the is the hot plate uh, is the hot plate in calibration? Uh, contact process engineering. Okay. So uh, is this the third adjustment? Okay. Contact process engineering. So if you have to calibrate it too much, you go and get help. Um, and then adjust temperature per specification in data and enter new data table. Um, and there's a comments log somewhere. So this is kind of a well-defined process for out of control. So if you're going to put a control chart out, maybe you don't have to do it in this manner with a flow diagram. It doesn't always have to be in the detailed. It could be always call process engineering. Um, might not be such a good thing when you entered the data incorrectly. Uh, however, however, you will run into stupider things. I guarantee you. I guarantee you. If you get the job, yeah. Charts will be used to estimate process parameters, which are used to determine capability. All right. Now, we sort of assumed our means and our standard deviations there. However, if we go and make the plots themselves, we then can estimate the standard deviation from those statistics that are there. All right. Why this is done this way, I don't know. There's probably some historical reason. But quality control folks, particularly when dealing with control chart, usually when things are on a continuous scale of measurement, call things variables. And when they're on a discrete form where you've got counts or go, no go, or percentages, they recall those attributes. Um, uh, For some of you who might be taking simulation with Dr. Na, there are attributes and variables, and they have a different definition. Um, and you have to remember what time of day it is okay, to get the right answer. So um, it's difficult with things being stuff different at different times of day. Okay, uh, and it's harder when you're actually the guy talking with all kinds of people listening. Though it's uh, control chart design. So we've got that encompasses a selection of sample size, control charts, and sampling frequency. Okay, there are some things missing. Statistic, what statistic you're going to use as part of it, as well as the sample size, control limits, and sampling frequency. Frequency here meant how many times a day, an hour, a minute, if it's a machine, you're going to make your sample. So um, the selection, the statistic, and also more practically, the measured attribute you might want to decide, and even more broadly, the process you need to study. So, but when we talk about control chart design, we sort of assume we have a statistic um, as a discussion item. Um, this is stationary is a little sloppier here than you see in some of the more mathematical books. That shouldn't be a problem. Non-stationary, we can think of drifts without any sense of stable or fixed mean. Um, we in physics they talk about random walks, and uh, yesterday Kevin and I were talking about random walks. Cole too. Uh, that's a non-stationary process. It moves along. Manufactured products, we really want to sort of stay at a certain center point as it moves forward over time. We do have things, and the control charts are set up where the measurements are uncorrelated in any manner. Very often, measurements are autocorrelated. How long you spend in line uh, anywhere depends a whole lot how long the person in front of you spends in line. That's why when you start looking at where you push your grocery cart, you notice how much is in someone else's. Okay. uh, Unless you really want to talk to somebody who's checking out at the grocery store. Okay, when I was in high school, yeah, it's okay. All right, yeah, that's a little too personal story, but okay. uh, I, no, I, yeah, I don't want to tell that. No, okay. It's not, okay, yeah, all right. Uh, reasons why these control charts are popular. Um, you can sell it to people in industry. Just uh, that's that's a big part of it, and it makes a good story will work. Okay, proven technique for improving productivity. Um, yeah, if you have a careful process and it has some foundation, and you put enough attention towards the process and have the authority to make changes, you will make it better. And if the control charts are part of that, you can sell it that you're skilled and helpful. So, because you have a chart someone else doesn't. Um, yeah. So they're proven and reliable, and makes you look like you're working. You went to school if you use one. Uh, it's important. Uh, okay. Control charts are effective in defect prevention. Yeah. Um, there are two things. We talk about um, you can have a process that goes out of control and still be making parts within specifications. However, you know a problem is occurring. It just isn't biting you yet. It just isn't hurting you yet. So you can attend to it as with like physical symptoms. If you find yourself coughing, you might want to realize, pick up something at your next grocery stop to take care of it instead of waiting a long time, or take some care to uh, make sure that uh, you avoid certain circumstances. So yeah, even though it may not be debilitating. Uh, Control charts prevent unnecessary processes. Oh, of course, this is a big one, right? People don't. Your job title is machine adjuster, or you're not doing your job if you're. Uh, okay, you can be sitting around if you're a machine adjuster sometimes. uh, yeah. No. When I was a co-op student at GE, uh, I remember they did have people with the job title of machine adjuster, and some of the machines need a lot of adjustment because it's just kind of a weird design. But and while I just happened to be walking by the workstation, one woman there said, "Yeah, Frank, why don't you go tell Jim that?" And I was like walking between the two places anyway. Um, I want you to go tell Jim my machine needs adjustment. And the woman seemed kind of lazy. And I go talk to this guy Jim, and I said, Beulah, Beulah says her machine needs adjustment. And I, Jim tells me, you go tell Beulah I'm not there. And I said, should I tell her you said you weren't there? And he said, yeah, go tell her. I said you're not there. Um, So I go back to Beulah and I says, Jim says he's not there. And Beulah got up and got all the energy to run over and talk to Jim about it herself. Yeah. Uh, okay. So, uh, uh, yeah. Okay. So much about Beulah. Uh, I remember. Okay, yeah, better not say that. Our control charts provide diagnostic information. All right, we're plotting a statistic. It can form a pattern. We have these patterns that we can deal with. Uh, we have patterns called cycles, which are different than they are on Tuesday night. Why, why is this guy act so confused? He has to teach different meanings of words on different days of the week. Oh, I got somebody got a comment. Let's see. Actually, I prepared a process capability document. We were looking at uh, we were looking at initial impurities profile. I could predict the final product purity. The manufacturing supervisor once called me scared to see the when he got scared to see the initial impurities. I looked at my document and told him there was nothing to worry about. The final result came out good. Hey, so you can do forecasts of impurity levels on a process uh, with a control chart. Uh, and how about that? So, and that was uh, uh, the kinds of forecasts they don't cover in the second edition, right? Okay. so, so I see if I can remember the word from last night. Yeah. Okay. Well, that's good. So the diagnostic information is important, and information about process capability. So we have all these things we learned from control charts that are good, and some of the students have. Oh, make a mistake here. Oh, this is actually in chapter 5. Uh, where am I writing? All right. This is actually chapter 5 stuff. And this is chapter 5. However, they introduced a new chapter in the book. Um, back pen. Okay. Um, they introduced a new chapter in the book and made this chapter 5, and I didn't switch up the graphic on this page. 3 sigma control limits. Okay, if we have a 3, the probability of a type 1 error is, and type 1 error means almost the same thing as it did in statistics class. That's when you make the mistake of saying things are different, this time out of control, when they are in fact not. Okay, type 1 error, what's measured by alpha. Um, and if you happen to remember all the nasty Greek words, we reject the null hypothesis when the null hypothesis is indeed true. Hypothesis testing terms. And so now you can go look those up, and they're in chapter 4 in the book if you had possibly forgotten all those details. Probability limits. Well, it's good, and I mean, it's pretty much the same thing on different days of the week. Okay, so on Monday night, I'm getting ready for Monday night. Probability error, type 1 error probability is, so US style 3 is generally used. In Great Britain, they prefer to use probability limits, and they would use, instead of a 3 sigma control chart, a 3.09 sigma control chart. I don't know historically the reasoning why that was. However, the difference is when we're reacting Usually people will use that 3 sigma control limit. So that 1 in 400 kind of chance, 1 in 378 kind of chance there. Uh, However, sometimes you want to be a little aggressive getting at stuff. This is the situation. You've got a new process that you brought in, maybe a radically different technology, a new built machine. Sometimes because you do weird stuff like General Electric did, making light bulbs, you actually build those machines yourself. Okay. Um, and you have people whose job it is to verify that they're working who built them. So you move the machine across town uh, from the lab where they built it to the factory where it's going to run. And the people who built the machine kind of uh, haven't always wrote everything down right or uh, or got everything done right. So they come across town to work for a couple days, and if the machine is to verify it's all working right, and if the machine is working right, they like got nothing to do but like their homework in their night classes. No, so, it's true. When I took night class at Cleveland State, guy who worked with at GE said that's what he would do. But that's when he'd catch up on his homework in his night classes. So anyway, um, uh, typically, so you might want to run with 2 sigma limits. So you get the 2 sigma limits are you get 1 in 20 kind of false alarms on that. But you have people sitting around anyway, right? Ready to adjust things. And maybe they see something that the control chart doesn't observe. You know, okay, if it's a machine part, you find people look at stuff and it's like, the color is wrong. It's too blue. It must have got hot or some way. And they they'll believe the color changed more than the control chart. I yeah, okay. I don't have that story set up yet. Uh, I, I I did work someplace and I did argue that based on some statistics that things were indeed different. And also I observed that the parts were a different color. All right, admit. I have to go and see if I can lose that waiting room. Um, didn't get as far. Too many stupid stories. All right, ARL, average run length. For the run length distribution of a control chart, if you want to look in your stats book, we'll have a geometric distribution, which is well well described, and how long, how many steps, how many samples will take until we get an out of control signal. And it is just literally 1 over p, the probability of calling things out of control. So 1 over alpha when it's in control, 1 over 1 minus beta when it's out of control. Wow, probabilities of making type 1 and type 2 errors. So if you're really up on knowing what your stats book is, that all makes sense. Otherwise, you can look them up and see it agrees. But the 1 over p always works, even if you get confused on one of the alphas and the betas. Okay. And it can be used to do control charts. Now, there are other kinds of control charts that make use of the history of the data. Okay, previous points in history to see if there are trends and accumulate those that are in like chapter 9, I believe they start. Those control charts have more complicated formulas for a average run length. In fact, they're like horrible. But strictly defined, they're defined in a series of nested intervals. Like, okay. Yeah. So 1 out of 370 is the ARL not sub-zero. The in control state, the null hypothesis state in hypothesis testing book. Yeah, I guess when I went through this last, I didn't have that other. Why didn't I think of doing that? All right. Geometric. It's actually probably section 3.24. I stole this from an older book. I didn't update it. But you'll be able to see what a geometric distribution is. So, and geometric distributions are have a long right tail. Okay, skewed like a life type distribution. I yeah, I don't. Yeah, I don't know what you're taught about distribution types. Well, we accept any statistics class, and like the ones I teach at OLC, they don't have a long discussion of types of distributions. Um, uh, we've got some people upstairs moving some furniture. Uh, I, let's see. And geometric distribution, the standard deviation is approximately equal to the mean. That's we okay, there's some comments about what the geometric distribution looks like. It's not. Yeah, probably better to just put a picture of the geometric distribution up. Okay, sometimes this, in practical planning, average run length isn't what we most want to think of. We want to look at average time to signal. So we can talk about uh, time intervals, hours apart, for example, or days apart, um, just to realize how busy your machine adjusters are. Right? Unnecessarily. If they say they're there or not, I don't know. Yeah. When we're um, so the false alarm every 370 hours if we take one every hour. Um, Suppose we have a process shift, then we can calculate an average run length of um, 2.86, and we put the subscript 1 for the out of control state. And so we would detect things every 2.86 hours. And out of control might mean, strictly speaking, out of control and out of specification are two different things. Now, you realize the specifications come from the operating needs of a physical system outside of things. Uh, More often, what comes out of the design engineering lab, a design engineering office, right? They say this is the spec. Things should work. The control chart limits come out of the quality control office, right? The engineers judge this is how the machine operates. So different sets of engineers make different judgments, and they're totally unrelated. so, so they come from two different sources. One is the real machine making the stuff, and those engineers describing them, and the others are the needs as judged by a different set of engineers. And of course, the guys who make the spec limits think they're smarter always, but it's okay. You deal with that. Let's see. Suppose this is unacceptable and we've reached the detect out of control. Well, we can play around with things. We can uh, make a more sensitive process, and then we can get our run length shorter. So if we have a larger sample size, we can respond more quickly. So that's what this argument is, going through some numbers and running it through. So if we take a larger sample, we get a more sensitive control chart and get a more timely response. Um, we also can play around with uh, sampling frequency. Now, in design two, we can check every hour, um, or we could check every half hour. Um, each of those would work, and our average run length um, in hours, or average time to signal, um, you would want to check to see which was uh, faster. I'm thinking design two might want to work that out. We could work that out. Now, related to this is that design decision that we made between design one and design two. And this becomes rational subgroup. Subgroups are samples that should be selected um, so that assignable causes are present. The chance difference between subgroups are maximized, while the chance difference between two sizable assignable causes within a subgroup would be minimized. Um, in other words, we uh, are choosing our grouping of our sample. Uh, Sometimes we have different positions on the same machine making a process. Um, when I was at GE, a couple of workstations over from where Buell and Jim were, uh, they would have like 340 of these tubes put into an oven at the same time, and they made the seal, the vacuum furnace at the same time. And each of those positions reacted a little differently. Uh, so you had to take some care to get different parts around. Okay. So, and we're choosing subgroups. There are two general approaches here. So sample consists of units produced at the same time, consecutive units. Primary purpose is to detect process shifts. So that's one way. Um, and we can take a random sample of all the units produced since the last sample. Uh, um, so we might go back an hour to chase these things down. Now, you might not actually be in a situation where um, those parts are still available after an hour. They might be moved onward, but uh, however, you could have set asides in that time period. Um, and then we could use a control chart about related to decisions of acceptance of a product, effective detecting of out of control state, and back into an in control state uh, between samples. So trying to do set asides in the time period. Okay, if we make our sampling interval large enough, the claim between interval between, okay, if we stretch things out between an interval between the observations in the sample time wise, we'll likely get some of those assignable causes behaving randomly, so in a controlled manner, so that we actually get things appearing to be in control unnecessarily. And this is the author's claim, that you need to that this does happen, and this author has a lot of practical insights on this kind of stuff. So I I, I would judge that this can't happen, although I haven't been in the situation where I've observed it. And so yeah, a couple of different ways. So snapshot approach and random sample approach, uh, and the corresponding charts. So it can be done. So this is a picture of how we would do it in that sequential manner, and this is the random sample approach. So we have some cutesy pictures of those two ideas for rational subgroups. Uh, okay, I want to talk a little bit about this patterns in control charts. Uh, Tends to look somewhat non-random. We see some runs up uh, in a rundown. Um, we only 19 points are below the center line and only 6 are above of these 25. Following the fourth point, we see a increasing run up, and there's an unusually long run down here. So um, we there are runs rules on control charts, and we'll look at those a little. Okay, so if we see these runs, we can actually do a statistical test on: is it higher? Is it higher? Is it higher? Um, if it's enough times in sequence, higher, 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 it would be unusual in a random process. Okay, um, and we can say, it's not random anymore. There's a trend, and a cyclic pattern. Okay, so uh, goes up, goes down, goes up, goes down, goes up, goes down. These patterns could be uh, regular uh, in length here and still be called cyclic, which on Tuesday night is wrong, but okay. All right, those would be called seasonal on Tuesday night. so, so we merge both the cyclic on Tuesday night and the seasonal to call cyclic here, right? Uh, we generally, if you have a regular cyclic pattern, those are often very detectable, and then you can design around them or learn to live around them. Um, when I worked for General Electric, they when you make that synthetic sapphire stuff, it gets abrasive. So the tools you use to form it wear out over time more quickly than other places. So you would have a whole box of parts on a high end of a spec and another on a low end of a spec because the parts would wear and then they would. Uh, the other problem was you would have two mating parts and they would both be this um, synthetic sapphire and it'd both be worn out. Uh, in cyclic patterns. However, they weren't on the same frequency, but the people designed the parts assuming that they were random and there was actually some technical overlap between the parts so the two parts could be out of spec and not working. And of course, there wouldn't be any problems. They're purely random and you can put them together. However, you had two irregular cycles and every few weeks nothing fit and everything was in spec. And we had to go down we had to go to the other part of town and explain our problem and ask if they could what we could do. No. Now we had to call the guys from the next county over to come and tell them that they designed this stuff wrong. No, um, that they didn't realize that there was going to be a cyclic pattern. Uh, anyway, so the Western Electric Handbook, uh, which yeah, so old stuff, 1956. if you had a man born that year, he probably has gray hair, and I know. So uh, we suggest a set of decision rules. So we have some other things that we can call out of control. Because they're unusual, because we assume that things are random, and we can break our control limits up in zones. And if we have 3 sigma control limits, these will work if our system is our computed statistic is roughly normal. This all plays correctly. Um, so out of control when 1 point's outside the 3 sigma limits. 2 out of 3 points beyond the 2 sigma limits. Okay. 4 or 5 consecutive points at a distance of 1 sigma beyond the center line, or 8 consecutive points on one side of the center line. So yeah, you can play around with your some hand calculations in a normal table and make judgments about if you're in the zone and what's the probabilities and so forth, and see that these are somewhat unusual, assuming they're independent. And some folks at Western Electric back in the 50s went and sat and did that. Um, but there weren't pocket calculators back then, so it's a little more work. And okay, so there are actually an extended sense of sensitizing rules. maybe I, maybe my fried rice did my tongue in. I don't know. So we have the Western Electric rules previously, and we have yet some others, and we can test these, and uh, and you can put in an exam problem and say, are these points out of control in this picture, according to what rule? It is very annoying to do grade. However, most of the people understand it pretty well, so this is kind of an easy question. Uh, no calculations, just observe. Well, count. Uh, let's see. In general, care should be exercised in several decision rules simultaneously. Um, yeah, we're now, if we use multiple things, we sort of reduce, we have a new alpha based on the alphas of each of the other rules. So being they're running at all the same time, and we're assuming independence of the sensitizing rules, which isn't quite right. So we don't know. What I mean is, if we look at those, uh, this assumes that each of those sensitizing rules are done independently. When we go and we look back at those rules, here are the rules. Well, um, if we have 5 consecutive points beyond the 1 sigma limits, some of those might be beyond the 2 sigma limits, and you might get this warning instead of that one at the same time, even, right? And they might double up, so they're not truly independent, they're dependent. Alternating up and down, one side. So any non-random pattern, whatever we we'd like. So all of those, that independence isn't there. Um, and there's a reference to Champ and Woodall. Um, we can, of course, simulate all these rules with different states of randomness and actually run them together and see what they would be. Um, uh, and then get a true alpha running all these rules and having a computer check it. It doesn't even sound all that hard to sort of code up if you've got a random number generator. Okay. We don't assume random number generators in this class. Um, Now, if you have Dr. Na's class, you can assume a random number generator. uh, okay. The Woodall and Champ investigated average run length performance with veritizing, sensitizing rules. So they made some observations, and you can read those in. Okay. Um, well, we get false alarm rates on these things, so um, um, well, you know, it kind of isn't fair to talk about Woodall in '87 compared to he had just a lot more stuff available to him than the Western Electric guys had in '56. Uh, okay, I mean these guys had 1987. They had IBM compatible computer running, um, probably running spreadsheet and a few other specialty statistics programs that they could play around with. The guys in '56, just playing around with their normal table. Uh, phase 1 and 2 control chart applications. Phase 1 is a retrospective analysis of process data to construct trial control limits. Okay. Uh, we have the charts. We have the machine. We run it. Oh, we have data. We can calculate the numbers to plot a control chart. We can take those numbers and we can put the control limits on it. So we can make the data plots first, and then in phase 1, draw the control limits in it. And here is this is somehow that doesn't seem right. However, it actually is a good idea because we're working from like a whole ignorance point of view, and we'll have trial limits. If we see something's out of control, we realize our system is not in control. And we can go back and guess based on time, which caused what caused the changes to set things out of control. And so we can look for process shifts and this term, which is a technical term, but really isn't well defined. Uh, Outliers, those things that don't fit in our model. Uh, and measurement errors, data entry errors, what have you. So we can, uh, by trying out this thing that theoretically works in a different case, the monitoring case, as a trial case, we have a very useful tool, right? And we'd like to, if we're bringing a new process on or modifying it, give it to someone and say it's in control if you do these things. And all is good. Not all is good. Uh, uh, and a phase 2 control chart is actually what we more often talk about. We monitor a process. We know it's running. We believe it's in control, and we check that process with it. And we assume it's stable and workable and so forth. So this is assumed in control. This is checking to see if we're in control. This is a new trial situation. This is an older effective situation. Uh, 826 and a discussion of the rest of the Magnificent Seven. I didn't, so I got rambling on control charts. I didn't think I would have enough to finish my 2.5 hours, which I'm supposed to have, and I didn't, so I was right. However, the boss has other things to complain about than me letting you out at 8:26, right? He's got a lot to complain about. No. Do you want to hear more about Beulah? No. Okay. Oh, anyway, uh, did you know? We talked about this list already, and maybe and the place it came out of Ishikawa's Guide to Quality Control, and came out of 60s Japan, and I, I've only spent a few hours in Japan, and it was at the airports. Okay, I mean, I don't know Japan, and I don't know how things were in the 50s and 60s, but I do know some stories that they used to broadcast nationwide on shortwave radio programs on quality control so people could study them. They were serious about this stuff. They bought into Deming and Duran and believed it and thought it would be, best for their nation. Okay. Yeah. All, all right. Thank God for Deming that Japan believed his message of prosperity and peace, that we'll work on making good stuff. Nobody will want to go to war with it. We don't have to go to war to get rich. We we just work. We go to work in a factory, sell good stuff. We have peace and prosperity. It's all good. And it works. It works. It works. Uh, you um, there were some people who seriously nominated um, Deming for sainthood, and then somebody says, in perspective, he found a way to make Japan peaceful, prosperous, and is like, well, yeah, yeah. I mean, I've got some people in the U.S. upset that they lost market shares. It's like, oh, yeah, we'll do that. All right, check sheet. Yeah, this is one check sheet. We can describe part number, location study analysis. So we look at parts, and we look at defects, and we eventually can check a box every month and then summarize it and still call it a check sheet about and then we can of course look over time which kinds of defects we have on the machine or a process. And there are other check sheets, I believe, too. So they come in different forms. Oh, yeah, I didn't show any more of that. Yeah, we'll leave the Pareto chart. We'll stop here. I like to talk about this more. No, I really do. I, okay. Some things I like to talk about. Oh, you've gathered that. Some things I don't want to talk about. Don't want to say any more about Beulah. No. What are you saying about Beulah? Okay. Yeah. Oh. Yeah. So we're done for the week. Okay. 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 Okay.